tuning is a skilled job. Every string has to be at a precise tension to produce the right note. The tension is altered by turning the square-ended pegs with a key, and the notes are compared by ear with one another and with a tuning fork. But could a machine do the job just as well as Brian here? Well, we've had a letter from Ian Runnacles, who's a teacher in Bury St Edmunds, and he writes and says that he and his wife find it difficult to find piano tuners in their area, and he proposes a micro-controlled machine. I have in mind, he says, a device about the size of an electric drill which could count vibrations, compare them with stored scale vibrations, and instruct a motor to turn a head held on to the tuning pins. Well, this programme is about getting micros into new products, a glimpse at some of the steps involved in turning an idea into a reality. Clearly, the first step must be a feasibility study. Will the idea work at all? And we thought it would be interesting to look at the idea of the electronic piano tuner to see if a micro could do the job. So we approached Brighton Technical College, which is one of the relatively few places in the country where they have practical courses for technicians in the use of microprocessors. Students, many of them from local firms, learn how to program micros to perform various practical tasks. And we asked Bill Davis, who's a principal lecturer at the college, to do a feasibility study for us. And this is what he produced. It's known in the trade as a breadboard, a working version of something which would eventually be reduced down to perhaps a few chips in a final product. Now remember, the fundamental parts of any computer system are input sensors, a central processor with a program of instructions in its memory, and some kind of output device. And in our mock-up here, what we've got is a microphone which listens to the piano being tuned. The sound comes here where it's converted into a signal which the computer can recognize. It can then refer to the program which is stored here in a memory chip and then control this simulation of a motor. And the program is the key. In essence, it tells the computer to test the note coming in and then compare it with the note, the frequency, held in its memory. And if the two are the same, it tells the motor not to do anything. But if the answer to the question, are they the same, is no, then it asks, is it higher? And if the answer is yes, then it instructs the motor to turn anti-clockwise. But if the answer to the question, is it higher, is no, then it instructs the motor to turn clockwise. And after each test, it goes back to the top and it asks the questions all over again. Now, this is a simplified version of the real program, but the whole thing was typed in at a keyboard, and Bill Davis has used a standard microprocessor board of the kind that he uses with his students at the college, and he's here with me. Let's have a quick try of the machine. Come on, get to work, tune for us and see if the motor will turn.
That's indicating that it will turn anti-clockwise and flatten the note.
Yes. It's stronger than you. There you are. It's going. That's
turn
it.
it clockwise and sharpen the note.
Did it take a long time?
Something like about 20 hours to write the software and a further 20 hours to test and debug the software.
But was that very complicated, or could one of your students have done it?
No, quite feasible for a student to have tackled the project from beginning to end.
Now, which was the more difficult, having something sensitive enough to the sound or strong enough to tighten things?
The most difficult part is the mechanical engineering of finding the motor to actually turn the key.
Is the other problem the bit of having the sensitive hearing that, after all, the human ear has? Can the computer match that?
Yes, I think the computer could match it in sensitivity. We can make it as sensitive as you require.
Well, it isn't going on the market yet, but you never know. Unlikely, of course, that that kind of direct mechanical piano tuner would be a practical proposition as a cheap consumer product. There are doubts about its accuracy. The human ear, as I've said, is very sensitive. And there is the question of the ability of a cheap motor to give the kind of control of the twisting of those pegs that Brian can give. But it has been suggested that a more upmarket version could be useful, say in a piano-making factory, to tune the strings of a new piano. After all, if you have new pianos, they don't need to be accurately tuned, since they will need tuning again when they reach the retailer. And then there could be a simplified system which doesn't turn the pegs, but it tells you on a screen whether the note is right or not, and then you do the rest. And we've heard that one of those is actually going on the market. But assuming that the idea you have is realistic, the second question you ask yourself is, what is the market? And the third is, how do you get the capital together to develop the idea into a proper working prototype? Let me show you an example. Take an object like this. Now that is a bicycle trip computer. And if you think about it, there would be a market if you could make it cheaply enough, and the makers are aiming at a price of between £20 and £30. What does it do? Well, it tells you the average speed that you've travelled, the miles you've travelled, the maximum speed you've gone, how long you've been bicycling, all the sort of thing that a lad on a bike would like to know. And all the circuitry is held on this one flexible circuit board, just one single chip computer. Let me show you something even more fascinating. Here's Roy Knott, and this is his baby. He's designed this. This is a product just about to hit the market. It's called sonic tape. It's not a camera. It's an electronic tape measure. It's the brainchild of Roy and his partner, who've more or less staked everything they have on it. And what it does is this. You point it at a flat surface like a wall, and you push a button, and it reads the distance from itself, from the back of itself, to the wall. It works by sending a beam of ultrasound out and measuring the time it takes to bounce back from a flat surface. Now, this would have to be very cheap indeed, it seems to me, to be a real challenge to a tape measure. So first of all, does it work?
Oh, yes, yes.
Now, how much could you put it on the market for?
We're hoping to put it on the market for around £80.
So a man who would normally take a friend and a tape measure, you think, would be prepared to spend 80, not to have to take the friend and to do the job with it?
That's right.
But who would he be? I mean, are you sure there is a market?
He would be a surveyor, a estate agent, a carpet fitter, a builder, an architect.
But how have you explored this market? I mean, just by asking people, or?
Yes, we've done a full market survey on this product, and the response has been overwhelming.
So you see everybody who goes and measures not taking Fred with him to hold the other end of the measure. Right, but how did you get the money for that, and did it cost you a fortune to develop it?
I've used a lot of my own capital on this device, and we have been developing the device for 3 years.
But when it was just a twinkle in your eye, was it difficult to persuade people that it was a good idea? But people like bank managers.
We go into a bank manager and measure his office first of all, and you take a tape with you as well, and he's convinced then.
Ah, well, of course, it's very easy to demonstrate. Now, once you are convinced that the product will work and that there is a market and that you can get some money together, then obviously the next step is development. And we've been to see a more complex system, which is being developed in a rather unusual setting. This is Rest Park, the stately home of the National Institute of Agricultural Engineers at Silsoe in Bedfordshire. I bet your cucumber plants didn't look like that on February the 6th. Neither did mine. But you see, these ones have an advantage because they are being grown in a glasshouse where the environment is controlled by a small computer. In a sense, a glasshouse that can think for itself, that knows what's going on around it, that can respond and even anticipate. A range of sensors monitor the conditions, the temperature inside and outside, the wind speed and direction, and the amount of solar radiation, because this affects photosynthesis. The signals from each sensor are then converted by simple circuitry into a form which the computer can understand. The plants are grown in soil-free, they call them hydroponic conditions, and the computer needs to know the acidity and the amount of nutrient in the water in order to control them. So these are measured constantly with probes which dip into the liquid flowing around the system. The computer controls the heat to the radiators. Alternatively, if the sun makes it too hot, then the ventilators open automatically on one side or the other, depending on the wind conditions. And then, to keep the plants properly fed and watered, the computer commands small pumps to pump in chemicals to adjust the nutrient balance. The point of juggling all these things, of course, is money.
You minimise the amount of energy you require to maintain the climate in the glasshouse. You do this because the computer is accurately monitoring and controlling in a way that the previous control systems was unable to do.
Well, put a price on that. I mean, how much would you save in an average greenhouse by having this system instead of the old one?
Typically, a heating cost for 1 acre of tomatoes would be about £20,000. And if you were running at 1 degree C higher than you should be, then this would cost you £2,000 an acre in wasted heat, because you'd get no commensurate return from your crop. And if you had 5 acres of greenhouses, then the saving in fuel, if you were achieving this sort of waste, could be repaid in about 18 months.
In other words, you could install the system and within a year or 18 months it would pay for itself.
Oh, yes.
And you would be getting better plants or earlier plants or stronger plants? Or...
You'd be getting better plants, they'd be grown more uniformly, and so you'd be getting maximum production from all your plants.
Well, now let's go and meet your computer. Now, in relation to the glasshouse, that is a sizable computer.
Yes, it's much bigger than is necessary to control the glasshouse that you've seen, but we're using it for developing programs that can be used in other computers which are more suitable for controlling a commercial glasshouse.
In other words, you're developing the product.
That's right, yes.
So what's Howard actually doing at this moment?
Yes. He's writing a monitoring and control program that can be stored in EEPROM, which you can see there on the machine, and then when that's been checked, it can be removed from there and plugged into the other computer.
And the program he's writing is based on the experience of what you've actually achieved with your own glasshouse?
That's right, yes.
Well, Howard, can we see the product?
Yes, well, this is just finished programming. Take that out of there. This is the EEPROM, which will go into the microprocessing board.
Well, show us where it goes. And then this then is the little computer the sort of professional grower would buy in order to control his greenhouse. I mean, more than one, I imagine.
That's right, yes. This would be capable of controlling several acres of greenhouses. Of course, it would depend on the size of the holding, but typically 4 to 5 acres.
Well, did you know anything about computers when you started this work?
Very little.
What did you find the difficult bit?
Well, the most difficult bit, as is the case with many computers, is understanding the manuals that are supplied with the machine and giving the instructions on how to operate it.
Is it worth the trouble?
Oh yes, absolutely, because once the system's installed, then it provides you with a tremendous amount of power to do a whole range of things that you couldn't do previously with orthodox controllers.
And indeed, that work is leading to a British commercial product later in the year, but already there are Dutch competitors. Which brings us to the fourth question, the risk of getting involved with micros as well as the risk of not getting involved. The micro component manufacturers are always pointing out that in just the same way as their products are doubling in sophistication every year, so will the understanding of someone who's already become involved with micros. Your first product may not be all that good, but next year you'll be able to develop a much better product because you will have had that much more experience. So it's important to look into the business of getting in on the micro act now to get on the learning curve. For if you don't, someone else surely will. And in this business, lead time is often crucial. Yet, getting involved is risky and can be expensive. Fortunately, help is available in the form of government grants, not only for advice, but also for development. And here's the story of one man on Merseyside who's been along the learning curve and who has sought that help and has taken the risks. John Goodwin's family engineering firm at Ellesmere Port is in an area hard hit by the recession. Most of the business he's built up over the years is in precision engineering subcontract work that is getting harder to find. In a search for greater productivity a few years ago, he looked at electronic measuring devices which he could fit to his own aging machines to make them more accurate. First he tried American, but since he dabbled as an amateur in electronics, he decided he could do better himself and started making his own micro-controlled system. Optical sensors screwed onto each machine feed the micro with a more precise measure of its movement than its own worn mechanical scales ever could. The engineer punches in the distance he wants the part to move in each direction. John's design had one simple advantage over the American machine.
What you do, you wind the machine by hand, in this case, until you see zeros. Because it's much easier to see a zero than it is to see a lot of long, complicated numbers.
What started as a modest attempt to help his own engineers led to John developing and selling a new product. But how did he get started?
It was very fortunate that when we started getting excited about micros and the prices started coming down, that the government introduced this MAP scheme for helping industry and encouraging people to look into micros. So we took advantage of that and we received £2,000, which was quite a nice sum of money, but nothing like the money that we've had to spend ourselves.
One customer has been British Rail, and they've driven a hard bargain. Railway wheels have metal tyres which wear down in time and have to be replaced. New tyres have to fit exactly because a loose fit could cause disaster. At Crewe railway workshops, the old steel tyres are cut off and the wheel diameters have to be measured precisely. John Goodwin combined his electronics and his engineering skills to design this enormous micrometer, able to do the job quickly to the nearest thousandth of an inch. The result determines the internal dimensions of the new rim, which is being machined nearby. This too is measured with another of his machines. Again, the result is a job made easier and with fewer errors. Once machined, the rim is heated up to expand it and then mated with the wheel. When the rim contracts, the two are locked and nothing but friction holds them together.
Well, the British Rail job, obviously, we've taken a big risk on that one, but of course we're looking to the future. We only got £6,000 for the job, but it's cost more like £18,000 to develop it. But we're hoping that when the 12 systems are required in the future, that we will be there picking up the order.
There are now some welcome new jobs in the factory, assembling the circuit boards for the new product. The work on the software for these was done with the help of the electronics department of Liverpool University. A good design was one thing, but dealing with the electronics components industry a couple of years ago was quite another.
We received the data, did a lot of study and a lot of programming at great expense, and immediately the program was complete, I hopped on the plane to Los Angeles and deposited it on the desk of the person who was going to do the building of the chip for me. And when I got there, he said, "I'm sorry, we can't make that component." So that was a bit of a blow. So I had to fly back again and get going on another component that they could make. And we had to go through all the software program again, because although the program is similar, it is different. So the whole thing had to be rewritten for a different device. So we had to hot foot on the plane again to Los Angeles to get the second one going. And then, of course, there's a delay. There's a 6 weeks minimum delay before you get prototypes. And then there's 12 weeks delay before you get the finalized microprocessor.
But as his experience and confidence in micros has grown, so has the range and the sophistication of the products he's made. The latest is a complete control system which can be bolted onto a conventional milling machine to make it work automatically. John hopes that this will appeal to small firms, offering them a cheap way into the computer age at a time when the engineering industry is having its worst fall in production since the 30s. But you see, John Goodwin had to go to America for his chips, had physically to take the programming work there to get memory chips made. And yet we've seen that it's possible to program the memory chips on the spot in a development system. Chips to work the piano tuner or the greenhouse controller, and just take them out and plug them into the product. So why did he have to go to the States? Well, to help me sort this one out, here's Jeff Vincent, our software consultant. As I understand it, this is the golden road to riches in this field. You develop your product, you reach that point, and then you have a choice of two routes. What's this one?
That's the mask ROM route.
So you put some money down and you do the masking. What's that?
Well, that involves the manufacturer making a pattern of electrical connections that represents the program.
And what does he finish with?
Well, that mask is used in the actual manufacture of the chip, so he can produce hundreds or thousands off of that chip very cheaply.
And what does that look like? Give me a chip.
It's one of those.
Now, suppose there's something wrong with that. I mean, suppose there's an error in it, things go wrong in whatever product it's in. What do you do then?
Well, then you've got to go through the whole masking process again.
I mean, you spend more money, another injection of cash, go through all that operation, and you finish up, you hope, with one which works properly.
That's right.
Now, is that common, that there are bugs in the system and you have to do it all again?
It's reasonably common.
And you've spent a great deal of money because you've had to buy them all before you've really started selling anything.
That's right.
Yeah. Well, what's the alternative route?
Well, the alternative route is to use this device, which is an EEPROM. Now, that's an erasable, programmable ROM, and you can program that yourself.
Well, that's what we saw being done in the glasshouse, didn't
That's
we?
right, yes.
Well, why doesn't everyone do that rather than go on this expensive route?
Well, for certain applications, this route can work out very cheaply. For instance, for mass consumer products, things that aren't too complex, like the cycle computer or even up to a washing machine, once you've paid the original mask cost, this can work out very cheaply.
Yes.
If you use a single-chip microcomputer, which has got not only the program, but all the computer parts on a single chip, that can be less than £1 a chip.
And this is for the very sophisticated thing?
Medium sophistication, yes, and upwards.
But getting cheaper?
Getting cheaper, yes. Those EEPROMs are getting cheaper all the time, and if you've got something like an industrial application or at the greenhouse, EEPROMs are a very attractive alternative, even up to tens of thousands.
Good, well, thank you very much. But you see, in this country, we've not been too successful in getting micros into mass consumer products. After all, the first pocket calculator was British, and yet it's the Japanese who've dominated the market. And one of the problem areas has been in factories where mechanical products have traditionally been made, and new micro-based alternatives have been introduced too slowly or too late. The cash register market is a classic example. Britain's last cash register manufacturer went out of business last year, year after a valiant attempt to get into the micro market against a flood of Japanese competition. And they admit that they were about 2 years too late. Now, one example of a company which does seem to have successfully achieved converting from manufacturing mechanical devices to manufacturing electronic equivalents is the one which makes these time clocks. This model was first introduced in 1903. This one, Mr. Noisy, in 1937. It has some 200 moving parts. But now there is this micro version with only one moving part, which is able to do many more things, including feeding information directly into the payroll. And we shall, in fact, be seeing it in action in a later programme, because we're going to see it at British Leyland's Land Rover plant. But I want you to meet the managing director of the company which makes those machines, John Parsons. Now, I'm talking about changing into the world of the micro. Isn't it an extraordinarily difficult thing, though, to go from the mechanical to the micro, to persuade people to work for you?
It can be difficult, but indeed it is a motivating force as well, because the people see they're being associated with a developing technology and a new idea. Because you're not just saying we're going to do what we've always done in a different way. You've got to offer something more. Well, that's right, Brian. I think it's particularly important when one is developing a micro-based product to relate it to the market needs, to go out and see what business really needs and then develop a product to suit that. In other words, a time clock can do a great deal more than clocking in and out if you've put a micro on it. But how do you persuade the people who buy it to know that? I mean, they may not recognise the need. Well, indeed, and that's one of the difficult features of the development of a new product of this type. But it is important to analyse what the market does need and act almost as a management consultant in this field. As well as a salesman? As well as a salesman, yes. But having decided to do it, you can't, like you could in the old days, start, you know, invent a machine and say, right, we can sell that for the next 30 years. Well, that's right, and of course this brings other and new pressures into the business development scene, because the time scale is much contracted. And it's constant development. Constant development, constant enhancement, and perhaps only a few months between generations of the same model. And of course somebody has to pay for it. Well, now the government will help in the payment of development. Jan Stewart of the DOI is with us, back on the old MAP scheme and things. Now, you told us last time that the government offers money for advice. When it gets to development, how much money will the government offer?
It's not so much how much, it's the percentage. The MAP scheme offers 25% of the total development costs. And are all the things we've seen in this programme the kind of things that you might expect to get 25% help with the development cost? Yes, every one of the applications we've seen so far in this programme is one that would be eligible. Obviously, it depends to a large extent on the particular manufacturer and the details of it. Well, when you come asking for the grant, do you have just to have an idea, or have you to be able to say we know there's a market, or what kind of evidence have you got to bring? Well, you've got to have a little bit more than just an idea, and that's why we were talking about MAPCON studies, the feasibility studies, because at the end of that you would have a clear idea of the feasibility of developing a particular application. And then with luck you get the loot. Certainly, it doesn't take long. Splendid. Well, thank you very much indeed. Now, next week, we shall be looking at manufacturing industry, and in particular at flexible and more competitive methods of production which microelectronics make possible. I hope you'll watch. Goodbye.